I'm going to speak a little about our generators, but I will also speak initially about wind power. What you see there is a picture of our first commercial turbine on the left, and what we do nowadays for a living on the right. And as you can see, not only did the dimensions change a lot, but also the equipment that you need to manage your equipment. We speak here offshore equipment that you don't just pull out of your garage. This is a wind market, how it has developed over the years. As it is now, it's a market of about 40,000 megawatts a year. Roughly speaking, a megawatt of turbine will cost you €1 million. So in round figures, we work in a 40 billion euro market. And as you can see, not much happened until 95. That's actually not the case. That's just a matter of the scaling. So in order to see what really happened, it makes a better overview to plot it with a semi-log scale. So I have here the vertical scale as a logarithmic. And this is how the market went over the years on a log scale. We had a very steep growth in the beginning, a decline, strong growth, the world crisis, and now we are looking into continued growth again. I call these phases Disneyland. 180% growth a year. That was great fun. It's not so difficult to grow very fast when your starting point is zero. But still it was a significant market. It happened in California. And California, of course, was driven by tax arrangements. So when the California government discovered in 1986 that it was probably getting to be too lucrative, and by the way, we did sell turbines. No, I don't think to Roger Daltrey, but we certainly had a turbine sold to Eric Clapton. So we also took care of his tax. Then we had the mass extinction. That was really serious. On the 1st of June 1985, there were 20 wind turbine manufacturers in Denmark. On the 1st of June 1987, there was one left. So it was indeed a mass extinction. Then we had 20 years of strong growth, 30% a year. Great fun. The world crisis, and now we are looking into steady growth. Roughly speaking, 10% a year is predicted for the wind industry. This is our own first turbine, the one you saw before, seen from another angle, put up in 1980, has run since then. So it's a good machine, has produced about 600,000 kilowatt hours over those 34 years. We sold one of those 30 kilowatts to the US, and I don't have any better picture than this one here. But that's the one down there. All the others in this picture are 65 kilowatts. And we bought it back from the US in 1991, because in 91 we did the world's first offshore wind farm. And when we did that, we did a line-up of our models outside the factory. So what you see on the far left is the first offshore turbine in the world before it goes out to sea. And what you see on the far right is a machine we bought back so that we could show our people and the press, this is where we came from, this is how we moved in the years. And we still have it. It's very nice. The baby bonus, it's called. This is the first brochure. That's the brochure by which we sold this machine. It's a wonderful piece. I still have it. It's from 1980. And underneath the tall picture is kind of the text you write when you start a new industry. The people that did this in bonus sat down and said, what do we write about this new product that's going to make our new life? And what they wrote is, don't you also think it's beautiful? I mean, that's kind of cool as a starting remark. Now we are going to start an industry. And this is how they look nowadays. So after 30 years, still a lot of family relations, 3 blades upwind rotor, but much larger. And on the inside, they nowadays have permanent magnet direct drive technology. And that's, of course, the main subject of today's talk. That was then. This is now. And if you look at it, the most dramatic thing in the wind industry, basically over those 30 years, is the growth in size. What we see on the far left is the first turbine. What we see on the right is our 6 megawatt machine, which I'll get back to, compared with an Airbus A380, the largest aircraft in the world. If you look at it in another way, this is our rotor compared to the Airbus A380. So it is really a substantial piece of equipment. When you stand at the blade mold and clap your hands, it takes more than half a second for the echo to get back from the wall at the other end of the mold. People look this big down there. And this is how the blades developed. The blade on the top is not the longest blade, but it's our best-selling blade today. It's a 53-meter blade. And what you see on the bottom, that little thing, is the blade from the first 30 kilowatt, 10-meter machine 30 years ago. If we scale it, it looks like that. And that gives you maybe a better impression of how much the industry actually developed. And as you can see, the new blade is much more slender. We say in our terms that it has lower solidity. What you can't see is that it has completely new aerodynamic profiles that we developed ourselves, mainly by the use of Delft University wind tunnel. But what you can get an impression of is that we are turning flexibility, which is in principle a problem. If the blades are too flexible, they could hit the tower. We turn that into an asset because we curve the blade like a scimitar, krumsabel, so that when the a wind gust hits the outer part of the blade, it not only bends, but because of this curvature, it also can't help twisting. This bent twist coupling is a passive means of controlling loads under gusty conditions. You don't need flaps or piezoelectric actuators or electrical wiring or anything. You just let the structure itself do the work of unloading when there is a gust. And this is the nacelle on the top of the turbine from this very first turbine we saw, and at the bottom, our best-selling machine today at 3 megawatt. The top one, 30 kilowatts, 10-meter rotor, 1.3 tons. The one at the bottom, 3,000 kilowatts, 100 meters rotor, 73 tons. The kilowatts and the diameter fit. The diameter went up by a factor of 10. That means that the area capturing the energy went up by a factor of 100, and the power went up by a factor of 100, so it all fits. Okay? Given that it all fits, couldn't we just have scaled up the old machine? Why did we spend those 30 years of engineering? Why didn't we just say, oh, the old machine works, still working. We should just have scaled it up. Well, if we had scaled it up, it would look like that. And instead of having a 73-ton machine, we would have had a 1,300-ton machine. That is what 30 years of innovation did on the machine design. This is our best-selling offshore machine. 75% or so of all the machines that go up now offshore are this type here. A 3.6 megawatt, 120-meter machine. The main parts you can see I pointed out here are the hub, where the blades are mounted, the main shaft, the gearbox, and the generator. The gearbox is the weak point. They do get manufactured, they do work, but when we go to really big machines, such gearboxes become a very specialized piece of work. At the moment, I think there's one grinding machine in Europe that can do ring gears bigger than 6 megawatts, one machine. So they become highly specialized, and if you look at the failure risk, such a gearbox, even at a 3.6 level, has 13 gear wheels and 22 bearings. Now, if you take the survival probability, you take the survival probability of each of those and multiply them all with each other. Normally, when you design bearings, you have a 10% failure probability in the lifetime. That's the so-called L10 rule. Then the gearbox would surely fail. We work to a 1% failure rate. But even with a 1% failure rate, if you have a 99% survival probability, and you multiply that for those 35 units, 0.99 in the power of 35, you don't get very close to a unity. You do get a significant failure risk. So the direct drive has the benefit that it has 0 gear wheels and 1 bearing. Then you can say, well, does it need to have all those complexities? A 1986 standard gearbox, that's the highest number of gearboxes produced in the 80s was this type here. So in the first decade of the wind industry, they looked like that. They had 4 gear wheels and 6 bearings, and such a gearbox would weigh about a ton. Nowadays, they look like that. They have 13 gear wheels and 22 bearings, weigh about 35 tons. Why didn't we just stick to the old one and scale it up? Well, same logic as before on the nacelle. If we did that, if we did the 1980s version nowadays for a 3.6 rating, it would not weigh 35 tons, it would weigh 100 tons, which would mean that it would be prohibitive in weight on the machine. The machine would simply need to be too heavy to support it. Therefore, complexity comes as the means of keeping the weight and cost down, but complexity has an associated cost. When you look at what others have been doing, when Maersk was building the world's largest container ship, they had various options for the drivetrain. They could do diesel electric, so having a diesel, a number of diesels driving generators, driving one or more motors on the propeller shaft. Or they could do high-speed diesels plus a gearbox, 2 diesels on one shared gearbox, or they could do a direct drive diesel. Actually, they couldn't do a direct drive diesel, because at that time there was no direct drive diesel with 100 and some thousand horsepower that you need. So that option didn't exist. Well, actually it did. Together with Sulzer, they built the mother of all diesels, 109,000 horsepower. So they stuck to what was in principle the right solution, even though they had to do significant engineering work to get there. And the simple reason was, of course, that's how they maximize their reliability. And also, when you do a hydroelectric power station, you could say in principle, well, we could do a direct drive connection between the runner of the turbine and the generator, or we could have a geared drive. But in reality, there is no choice. They all look like that. They all have a direct connection between the runner and the generator. There is no choice. You cannot go to your board and say, yes, we are going to build this hydropower station with a calculated lifetime of 100 years, and here's the gearbox. Simply doesn't work. And that's, of course, what you need is reliability. In wind, that thinking is not new. We can no way claim fame in any way about that. One of the early pioneers of direct drives was Mr. Jacobs. He built wind turbines in the 1930s for the mainly for the American Midwest. Because in the Midwest in the 1930s, people had started seeing the wonders of electricity in the towns around them. Every town now had been electrified. There would be a movie theater, there would be electric light, and then they would go back to their farm and there would be nothing. So hundreds of thousands of farmers installed turbines like that, and this is a direct drive wind turbine. There were other types with gears, but these are the ones that survived. This type here is a 4 kilowatt. I think it's a 48 volt DC system. And interestingly enough, when I first traveled in the US to look at wind in the late 70s, you could still buy refrigerators, washing machines, vacuum cleaners to run at 48 volt DC because there was a legacy of the Midwest. Of course, it had died out again in the late 1930s, 1940s when they got grid connected out into the farms. But until then, these direct drive machines ran. And one of the really wonderful stories is that an American expedition put up one of those machines at a camp in Antarctica in, I think, the 30s, and then revisited the camp after 20 years in the 50s, and the turbine was still producing electricity and still able to charge batteries after having run for 20 years with nobody there in Antarctica. The only problem being that, first of all, the snow had drifted so that the tower was gone. And secondly, that the blades were heavily eroded by ice crystals on the leading edge. But other than that, a machine that ran for 20 years with absolutely no maintenance. In the more recent era, this nice machine was done in the early 80s in the US. A permanent magnet machine, 10 kilowatts, didn't work aerodynamically. They had aluminum blades. That doesn't work. But still, somebody got there long before us. Also, a German manufacturer, Enercon, is big. The biggest German manufacturer is high on direct drive machines, very, very competent and professional, but somewhat different from us because they use an electrically excited machine. We decided to go this way around 1999, and it took us 10 years. Because when you want to do such a project and you want to do it seriously, you need to go through a number of steps. When you have, at that time we had done geared machines for 20 years, That's where all our competences were. We had none in permanent magnet machines. We had none in direct drive. We had to go through all those steps, as you see there, from a concept idea and until a market launch. What you see on the left is more as a curious. That's the first patent application on this whole thing, dating from May 99. And what we did was that we confronted the main challenge head on. The main challenge is that geared drives are inherently, if you don't do something smart, they're cheaper. So you have this problem that you want to maximize the reliability, but the customers want the cheap solution and it has a gearbox, but that doesn't maximize reliability. So what do you then do? And of course what you do is to try and use the technologies that made geared drives cheaper to also work on generators. And there are basically two tricks, maybe three tricks. The most important is to get away from this being a project and into being a product. When we visited the people in the world in the early 2000s that did big machines, you would have meetings, you would have talks, and then you would have a factory tour. It was great. I loved it. And you walk around with super competent people, and the factory is full of sexy equipment, but they all have a name. This is for such and such a mine in Chile, that's for that and that cruise liner, this is for this and this open cast thing in China. They all have a name. And that's wrong. You cannot do serial production and low cost if things have a name. They need to be anonymous. You need to speak not a project, but a product. And then we did some technical choices. And the first one of them is that we selected an outer rotor topology. Of course, we started our life with inner rotors. Everybody that does electrical machines tend to go for inner rotors. But here you can see a comparison. I have two machines side by side, on the top without the rotor and then the bottom with the rotor. They have the same air gap dimension, 4 meters diameter, 1.4 meters air gap in the axial direction. But as you can see on the bottom, they have a very different physical dimension. So when you go for transporting equipment out of Denmark to Europe, and on the way south, you have a big constraint called the Elbe tunnel. And that Elbe tunnel has a maximum height being shipped through of 4.26 meters in diameter. Then I can assure you that 4.2 meters is good and 5 meters is bad. And the other and more important actually element is to say, in the effort to go for the product approach, we developed a segmented stator. Of course, segmented stators are well known. All big hydroelectric generators have a segmented stator. But the difference is that they typically are done with a completion of the winding after the stator has been installed. So you have open slots, and then you install the last bit of the winding when you have installed the stator. We needed to do a solution where the stator segments are indeed independent and don't need any kind of electrical wiring after they have been completed. And the solution to that was a single layer winding. That's kind of old-fashioned. The interesting thing was that the elements of the solutions needed to be dug out of literature from the 1920s and 30s. That's when single layer winding was common. But it works here. And this is how such a segment looks. And of course, as you can imagine, the big beauty is that you can install the coils from top down. Both the manual handling and also the automation opportunities are very, very different from when you were to do a complete machine. We did a greenfield study saying, what would it take us from we started stacking laminate and until we had a final completed machine ready to be dispatched, what would that take us? In round figures, with all the steps of stacking and coiling and bracing and VPIing and everything, in round figures, 42 days, 6 weeks. Now we do those things. They don't take up a slot in a factory of 10 by 10 meters. They take up a slot that's somewhat less in dimension than this table here. And then we assemble the machine in our factory, not in 42 days, but in 8 hours. So the benefit of this segmentation is huge, and that is what makes us take the step from working with a technology that has difficulties in competing to a technology that does indeed compete directly with geared technology. This is a magnet pole. The magnet poles are 25 centimeters, roughly 10 centimeters wide. Such a magnet pole can lift a car. So it's a dangerous piece of equipment. It's dangerous from its mechanical properties. You don't want your hand between that and any sort of magnetic equipment. And it's also potentially a risk. Nobody knows. But could there be something about strong magnetic fields and health? Nobody knows. But I know that when I was a boy, in my mother's ladies' magazines, you could buy armbands with magnets that supposedly had some effect on you. And therefore, at least people in some periods have believed that magnets mattered. And therefore, what we have built is this magnetizing robot, so that we buy the magnets completely encapsulated. You can see they are in a stainless steel cover, but as we say, cold. They are unmagnetized when we get them. And then this robot magnetizes and inserts them. Here's the insertion arrangement in one operation without humans' hands being involved. And that way you avoid the risk of somebody getting hurt by the magnetic forces, and you also avoid the risk of somebody discovering 10 or 20 years down the lines that these magnetic fields were indeed tricky. Magnets have been a subject of much discussion because of the magnet price hype we had in 2011. This is the peak we saw. I updated the figure on Tuesday with the latest prices. So this is very much up to the point. And what you would pay nowadays in round figures is about $41 on the open market per kilo for a grade N35H. If you buy it as a big user like Siemens, you pay considerably less. So there was a shock wave on the rare earth magnets, but to a large extent the impact of that is gone now, and the fluctuations of copper today actually mean more than the fluctuation on magnets. If we take one closer look at the magnet, this is how it is composed. You can see that the rare earth is about 30% of the whole. The rest is iron and boron. If you look at the cost, it's mainly neodymium, but there's also some dysprosium, and then 20% for production. The dysprosium is a tricky thing, because neodymium is not really rare. There are many deposits in the world, and many of them are outside China. Whereas dysprosium is indeed a rare earth. And here the trick is that when we started our project in 1999, and I looked at magnets with roughly 4% dysprosium. When we built the first machine, the magnets of that machine had 3.5% dysprosium. The machines we built now have 1% dysprosium, and in a few years it'll be gone. And that is actually the most important fact about the rare earth magnets. That is that of the two rare earth metals, one is not really rare, and the other one is disappearing from the magnets. But you could do an electrically excited machine, and we have done a design, and it can be done. But it doesn't work if magnets are cheaper than about 50 euros a kilo. Today we buy them at 30. If we had another hype, we could do the electrically excited. As it is at the moment, it makes no sense at all for us. This is how we cool our machine. What you see on the left is the machine, and we have something we call the liquid link. That's just a buzzword. It doesn't mean anything, but it does actually explain to some extent what it's about, which is that the machine has a big passive cooler on top, and you have a liquid, just water and glycol, that's cooled passively by the wind, and then passed through a heat exchanger inside the turbine, and then the actual cooling medium that goes through the winding is air. And the benefit of this is that it's totally enclosed, but we still have the primitive system of the air cooling, which is attractive because it's primitive. Because in such machines that operate for years without maintenance, simplicity is God. Here we see the nacelle from the top. What you see on the front is the big passive cooler, many square meters of radiator. And the effect of all of this, going from the initial situation where we did see some nice price reduction, but where we were still kind of in the grip of the conventional thinking of the suppliers. And until we, at the beginning of 2008, said, come on guys, you need to listen. We know about serial production much better than you do, because we do turbines all the time. We have hundreds of thousands of tons of equipment through the factory every year. You need to listen. We want the segments. We want so and so. The effect was like that. There was simply a quantum leap on cost. And the trick was segmentation and design for manufacturing. This is the result. That's how such a machine looks. A 75-meter blade, 25 tons. Such a blade is loaded with up to 20,000 kilonewton meters. Probably that doesn't mean so much for you, but the main thing is that if you were to load the blade with a car, if I was to load it with my old Volkswagen Golf, I would not get anywhere by just putting the Golf car on the tip of the blade. If I want to load the blade with a Golf car, I need a beam that's 2 kilometers long. Then I can suspend the Golf car on one end and try to hold the other end. That's what the blade root does. The direct drive system does give us big advantages because it's much lighter. This is a diagram of turbine sizes on the x-axis and weight on the y-axis. And as you can see with the direct drive system, we are way lower in weight than the rest of the market. That really matters when you go offshore. This is how such a machine looks, the team that built it. This is getting it out of the building. Sometimes people ask, why did you make it exactly 6.5 meters diameter? Why not something else? Well, that's where we have still a matchbox in our gate at each side. Taking it out, when I look at the number of tires on that trailer, I can't help feeling pleasure thinking about the guy that has to kick the tires every morning, has to walk down there and kick tires. That's what you meet on the road. Unloading from the ship that took it the last bit. Stalling tower. Lifting up the nacelle. The rotor up. The rotor going up. And here we are operating. Such a machine does, on average, in 3 days, what the first machine did in the first 34 years. So that's how far we got. On going forward, aluminium, smart magnets, magnets with differential composition so that you take account of where have the risk of demagnetization, winding overhangs that allow a taller coil and still stay within the same length. So there's a smart new, which you did not see in the 1920s literature, winding overhang coming up. And then in the long run, it may be that we do machines with concentrated windings. There are some challenges, but it allows for a higher power density. And then the 6 megawatt is not the end. This is a snapshot of a 10 megawatt machine. As I say, big boys' toys. Such a machine will have 210 meter diameter, so blades that are more than 100 meters long. And still getting cheaper and cheaper per produced kilowatt hour, because big machines like this big generator get cheaper with size when it comes to energy. Just as a concluding set of remarks, a few figures on Denmark. I work in a wind turbine manufacturer in Denmark. Denmark is a forefront country. We had 33% from wind last year. Over the winter, we had more than 50%. In January, more than 60% of electricity coming from wind. We had a turbine that ran for 89% at rated power in January. And we had some big projects that ran for also high 80s. And we had one single project in Denmark, the Anholt project, 400 megawatts offshore, where that single project did 8% of the whole country's electricity. That's kind of fun. When I started in 1976, the sweet dream was 10% from wind energy, if we are lucky, sometime in the future. Now, of course, the sweet dream shifted. The goalpost moves. Now it's 50%. and we'll get there. But there are some challenges. This is January this year. The light curve is the load, the dark curve is wind production. As you can see, there are times when we exceed. So storage is coming up. And finally, this is how the world energy mix will be if we trust the American Department of Energy from now, or rather some years back, and until 2030. I would like it to be different. I don't think that old people sitting in big departments somewhere shall decide how the world should move. If we can continue the innovation with people like you, we could cross this threshold where we become directly competitive with other electricity sources. And if we get there, we are not only serving political markets, we are serving the whole market. That is my ideal, that we get there where subsidies have disappeared. We are getting very close onshore. We'll be there within this decade, and we'll be there offshore next decade. That could that could change the energy world. That could make it look like that. That's what I work for. That's what you should hope I work for, because that's what your children are going to need. So, the good question, can we actually do that? Can we actually do innovation that can get there? And you all know the answer, what the answer has to be. We have to get there. We can get there, and we will get there. Thank you.